Hello guys, welcome to Physics Grad. In this video, we are going to learn about the concept of center of mass. Let's begin. In our previous lectures, we had already seen that the total momentum of a closed system, was given by capital P vector equal to summation over A mass times the velocity of each particle. But we know that in different inertial frames the velocity values will be different. Okay, in different inertial frames the velocity values will be different. So what does this imply? What is the consequence of this? So if you take two frame of reference in which one of them is moving with a certain velocity with respect to the other, and if you measure the velocity of each objects in the two different frame of references, you will measure different values for the velocity. Okay, that is what this statement means. So therefore, the momentum of a closed system P, therefore P has different values in different inertial frame of references. In different inertial frame of references. Okay. So to understand this better, consider a frame of reference, an inertial frame of reference K dash, which is moving with a velocity capital V relative to another frame of reference, inertial frame of reference K. Okay. Then we have using the Galileo's transformation formulae, we have VA is equal to VA dash plus V. Okay, so this is because if we have a particle which is moving with velocity VA and I observe it with two different frame of references K and K dash, where K dash is moving with respect to K with velocity V, then the velocity as observed by the frame of reference K will be the velocity observed by K dash plus the velocity of the frame K dash itself. That is what this equation tells us. Okay, so this implies that the total momentum P, which is given by summation over A MA VA, will become summation over A MA VA dash plus V, which is summation over A MA VA dash plus V into summation over A MA. Correct? Now this quantity I can call it as P dash, which is the total momentum with respect to frame of reference K dash. So therefore we have P equal to P dash plus V times summation over A MA. Right? Now if you notice, I can always choose a V. So we can choose a V such that P dash equal to 0. Okay. This is another way of saying that we can always choose a frame of reference K dash such that P dash becomes 0. So we can always choose a frame of reference K dash, okay, such that P dash becomes 0. Okay. So if we set P dash equal to 0 in this equation, what do we get? We get P equal to V times summation over A MA, and the V is given by P divided by summation A ma. Correct? Now before we proceed further, let us make note of some important points. So note, if total momentum is 0 in a given frame of reference, okay, then the system is said to be at rest relative to that frame. Okay, so let me write that down and explain it clearly. If P dash is equal to 0, that is the total momentum is 0 with respect to frame of reference K dash, okay, then the system is said to be at rest relative to that frame, relative to K dash. Okay, so what does this mean? Even if you consider that all the particles inside the closed systems are moving on their own, but the total momentum of the closed system, that is summation over MAVA dash, becomes 0, we say that the system as a whole is at rest. It doesn't mean that all the particles which constitute the systems should be at rest. All this means is that the total momentum is 0, implies we can say that the system as a whole is at rest. Okay, so the entire system, if you consider, it will not move. So what I mean is that if this is a system and this is made of some particles, okay, these particles may be moving around randomly on their own, but they are moving in such a way that their total momentum MAVA dash becomes equal to 0, implies that this entire system is going to remain in this particular region in space. Okay, so a good example would that be of a box containing gas particles. Okay, so we can consider this box, whatever is there inside this box, as a system, but we say that this box is not moving with respect to space. Okay, then the total momentum of this box must be 0. That is what this statement says. But if you consider a box containing gas wherein the entire box is moving with some velocity v, then its total momentum will not be 0, because every particle inside the box will have a component in the direction of v. Okay, a momentum component in the direction of v. So it will not get cancelled, and therefore the total momentum will not be 0. Okay, so that statement can be more precisely said as following. So similarly, v is the velocity of the motion as a whole. What I mean by this is that not every particle is going to have the same velocity given by capital V. I am talking about the entire system as a whole. Okay, so motion as a whole of a mechanical system whose momentum is not equal to 0, and that is what I explained in the case of this example. Alright, so therefore the law of conservation of momentum, it gives us a natural definition of rest and velocity as applied to mechanical system as a whole. Okay, so let me write that down. Therefore, law of conservation of momentum, okay, this gives a natural definition of rest and velocity as applied to mechanical systems as a whole. So we say, so what does law of conservation of momentum says? For a closed system, if the Lagrangian is independent of the position coordinates, so this law of conservation is valid if summation dou L by dou R is equal to 0. So this law of conservation of momentum for the total momentum is valid if this condition is satisfied. Okay. Once this is valid, this implies P is constant, which implies V is constant. Okay. And if P is 0, implies V is 0. And we define this condition as rest and this condition as, or this as the definition of velocity of the entire system as a whole. Okay. So we define this condition as the entire system being at rest and this condition as the entire system moving with a constant velocity. Alright. So we have this V equal to P by summation over A MA for the whole system. This is a definition which comes about as a consequence of law of conservation of momentum. Okay, for the whole system. But for a single particle, we know that, so for a single particle, we know that the velocity is given by the momentum of the particle divided by mu, where mu is the mass of the particle. Now if you compare this equation and this equation, what will we see? What do we see here? Okay, so comparing these, we can treat the entire system as a single particle, of mass mu given by summation over A MA. Because if you see mathematically, these equations form is the same. So if we define this as some mu, there is no way of saying whether we are dealing with a total system which consists of many particles or whether we are dealing with a single system. Both are equivalent, and that is what this statement is explaining. We can treat this equation as the equation which describes the velocity of a single particle whose mass is given by summation over A MA. Okay. So this implies mass of, so this we are going to define as mass of the entire system. So mass of entire system is equal to sum of individual sum of masses of individual particles, which is nothing but the additivity property. Additivity of mass. Okay. Now one more thing, if you notice, is the following. Our V is given by summation MA VA divided by summation MA, where this is nothing but the total momentum P. This can be written as summation MA d by dt RA divided by summation MA over A. This in turn can be written as d by dt of summation over A MA RA divided by summation over A MA. Now I am going to call this or denote this by the vector capital R, then we can note that this is equal to d by dt of R. Now for a single particle, V is equal to d by dt of R. Okay. If you notice the form of these two equations, I cannot say by just looking at this equation whether I am dealing with a single particle or whether I am dealing with the system. Okay. Because this is one vector, this is another vector, here also this is one vector, this is another vector, and here we are considering a single particle, here we are considering a system. But if I had not told you beforehand what is the meaning of this vector R, whether this vector R is defined in this way or not, then you will not be able to say whether this was for a single particle or whether it was for a system. Okay, so this implies the velocity of the system, as a whole, okay, is the rate of motion, in space of the point whose radius vector or position vector is R, and that is what I was saying here. So this is same as if there was a single particle whose position vector is given by capital R, okay, and that R is given by summation over A MA RA divided by summation over A MA. Okay, and this point whose position is given by this vector R is called the center of mass. Okay, so this point is called the center of mass. I'm going to denote it as COM. Okay. An important thing to note here is that this is an imaginary point. It is not a real point, as if there need not be an actual point inside the system whose position vector is given by capital R vector. But this is just an abstract concept wherein we say that the velocity of the system as a whole is the same as the velocity of an imaginary point whose position vector is given by capital R, which is defined in this manner. Okay, so note that this is an imaginary point. Alright, so therefore what we have here, we have that the law of conservation of momentum for a closed system implies that the center of mass of a system moves uniformly in a given straight line. Okay, let me write that down. So therefore the law of conservation of momentum, okay, for a closed system implies that center of mass of a system moves uniformly in a straight line. Why? Because if the momentum is conserved, which means V given by P by summation over AMA is also constant if P is constant. And if V is constant, this implies the point which is defined as center of mass is moving with a constant velocity, or in other words, it moves uniformly in a straight line. Okay, this is nothing but we can define this as the law of inertia for the system as a whole. So this is law of inertia for a system as a whole. For one particle we had that the particle's velocity should be constant, whereas here for a system the law of inertia says that the velocity of the center of mass should be constant. Okay, so this doesn't mean that the velocity of individual particles which constitute the system needs to be constant. All it is saying is that the total momentum must be a constant value, which implies the velocity of the center of mass also is going to be constant. Okay, so let us make note of these important points. For a closed system, we can always choose a frame of reference. We can always choose a frame of reference in which the center of mass is at rest. In which center of mass is at rest. Okay. This is the same as choosing K dash where P dash was equal to 0. This implies V dash given by P dash by summation over M is also 0, implies this V dash is the velocity of the center of mass, which is 0, which means center of mass is at rest. Okay. So what is the advantage of choosing a frame of reference wherein the center of mass is at rest? Okay, so doing this will simplify our analysis, as this eliminates a uniform rectilinear motion of the system as a whole. Because even if you consider this part, the mechanical properties of the system remains unchanged. Only thing that will be added is some complicated algebra. Okay, there will be some additional terms in the algebra related to this capital V as a result of the center of mass having constant velocity. But if we consider a frame of reference in which the center of mass is at rest, we can do away with this velocity component of the center of mass and therefore simplify the algebra. Okay, so always choosing a frame of reference for a closed system in which the center of mass is at rest will make our mathematical analysis easier. Okay, and this is an important point to remember. So as an example, let us again consider two particles whose masses are equal. Then due to gravity they will attract each other, and if initially they were separated with the distance which is infinitely large, and initially if you consider them to be at rest, then the total momentum initial will be 0, and if I consider this as entire two particles as a system as a whole, then this system is closed. Okay, and in our previous lecture we had seen that the momentum for this system is conserved, the total momentum is conserved, so P final should also be equal to 0. This implies the velocity at any time, okay, given by the total momentum at any time divided by summation of masses, which is 2m in this case, is going to be 0 because this P of t is conserved and it's a constant which is 0. This implies in this case the center of mass is at rest. And what is the center of mass? So if the position vector of this is r1, this is r2, then the center of mass position by definition is mr1 plus mr2 divided by m plus m, which is r1 plus r2 by 2, which is the geometric center of the two particles, and this point is going to be always at rest with respect to a frame of reference k wherein initial momentum was 0. But what if you have another frame of reference k dash where p dash initial was not equal to 0 but equal to some constant c? Then this would mean that v dash of t would be p dash of t by summation over m, which would imply v dash of t is equal to some constant c by 2m. Therefore, v dash of t is d by dt r dash of t, and therefore center of mass is no longer at rest. This means that if we observe the same thing with this frame of reference, what you will see is that after some time t, if this is moving with the velocity v in this direction, then after some time t, we will see this system like this. So this would have moved here. Okay, let me use a different color. So you will see a system which is like this, where this is translating with velocity v. Okay. All right. So using whatever we have done so far, we can define another useful quantity. So what is that? Let me write it down. If you consider the energy of the entire system, okay, so the energy of a mechanical system whose center of mass is at rest, okay, is called, it's defined as its internal energy. Okay, this means if I have some system which is made of many different particles whose center of mass, let's say which is over here, is at rest, then we know that these systems the particles inside the system can still be moving around. Only condition is that the total momentum should be 0, which implies these particles, which may be interacting with each other, will still have some kinetic energy and potential energy, and that energy is defined as its internal energy. Okay, so it's the energy of the mechanical system whose center of mass is at rest. Okay, so this includes the kinetic energy and potential energy, which is due to interaction of each of the particles. All right, so this E internal is given by summation MAVA square plus some U, okay, where U is dependent on position vectors r1, r2, ... Okay, so this is the potential energy, this is the kinetic energy of the system when the center of mass is at rest, and this together is defined as the internal energy. Okay, then what is going to be the total energy of the system when center of mass is moving with velocity v? Okay, so this implies total energy of a system with center of mass moving with velocity v. This will simply be E equal to half into mu v square plus EI, where this mu is summation over A MA. Because now every particle is going to have a velocity component v in the direction in which the center of mass is moving. like this. So this will be the additional kinetic energy term for the total energy of the system. So just to make it more concrete, let us prove this. Okay, so to prove this, consider frame of reference K in which the momentum, total momentum is 0, which means the center of mass is at rest with respect to frame of reference K, and K dash, which is another frame of reference, moving with velocity v with respect to K. Okay, then what is this? And so in this case the center of mass is moving with some velocity. Okay, so therefore the total energy in frame of reference E dash, okay, will be given by half into summation over A ma va dash square plus u, where va dash is now the velocity of individual particles. This is nothing but half into summation over A ma va minus v because of the Galileo's transformation plus u, this whole square. So this is equal to half into mu v square, okay, I'm just expanding this, minus 2 times half mu, which is 2 and half will get cancelled, so we have v dot summation over A ma va plus half ma va square plus u. Okay, I'm just expanding this term. Now if you notice, this is nothing but the internal energy. So this is the internal energy in K, where the center of mass is at rest. And since the total momentum, okay, since the total momentum with respect to the frame of reference K is 0, this total momentum is nothing but summation ma va, okay, and that is what we have here. So this term goes to 0, which means this entire term goes to 0, and what are we left with? We are left with half mu v square plus ei. Okay, so therefore the total energy of a system in a frame of reference in which the center of mass is moving with some velocity v, in this case the center of mass moves with velocity v in this direction if K dash moves with velocity v in this direction, okay, but when you take this magnitude square, the direction doesn't matter. So the total energy is equal to half into mu, which is the summation over all the masses, times velocity of the center of mass squared plus the internal energy, which is what we had written down here. Okay, alright, so that's it for this video. Thank you for watching. See you next time.